Hey everyone, welcome back for another Algebra 2 lesson. We're looking at some more trig stuff this week. You can see on your screen that we're going to be doing lesson 7.5 today, and we're going to be talking about how to graph other trig functions. Remember in last week's lesson that we talked about how to graph sine and cosine functions. So this week we're going to be looking mainly at tangent, but then we're also going to get into how do you graph the reciprocal functions for sine, cosine, and tangent. So how do you graph the reciprocal of sine, which is cosecant? How do you graph the reciprocal of cosine, which is secant? And how do you graph the reciprocal of tangent, which is cotangent? That is our essential question, is how do key features of a trig function relate to key features of other trig functions? So we're going to look at the formula for a trig function in general, like similar to last week when we looked at a sine or a cosine function is going to be in the format of a times sine or cosine of bx. We're going to learn the format for a trig function and then see how we can manipulate trig functions to come up with other trig functions. So let's jump into the warm-up for our lesson. So our warm-up says that we have these two functions. The first one is f of x, which is x plus c, and that's just a line. And our second function, g of x, is the reciprocal of that. It's 1 over x plus c. So part A says that we need to identify the zeros of each function. So in order to do the zeros, I'm actually going to pop this out, make it a little bit bigger, so it'll be easier to see. So the first one, the orange line, f of x. If you look at this line, you can see right now that it has a y-intercept. So it has a 0 on the y-axis of 0, 3, and it has an x-intercept. So it has a 0 on the x-axis of -3, 0. And hopefully you can see that this number 3 is related to the fact that this says x plus c and that c is 3. And if I were to change the c value, let's say I change c to be just 1, that the orange line now has a 0 at 0, 1 and -1, 0. And notice these 1s are still this c value. If I change c to be, let's say 5, that our zeros are now at 0, 5 and -5, 0. So I'm going to go back and just leave this at 3 where it was at the start, just so that I can answer my question a little bit better. Also, so we know that, so when c is 3, we know that the f function has a 0 on the y-axis of 3 and a 0 on the x-axis of -3. But we also need to talk about the g function, which is in blue. So the g function, 1 over x plus c, if we're looking for a 0 on the y-axis, let's see right here, 0.3 repeating, that's 1/3. So imagine if x right here was 0 and c is 3, we'd have 0 plus 3 in the denominator, which is 3, and then 1 over that, 1 over 3 is 0.3 repeating. I don't see any other, I don't see another x-intercept here. If I zoom out, if I trace along here, you can see my y value on this left side. It's small, but it's never 0. And over here on the right side, it's small, but it's still never going to get to 0. And that's because we have asymptotes, and that's going to come into part B of this problem. So I'm going to pop this window back in and then answer part A, identify the zeros of each function. So f of x has zeros at 0, 3 and -3, 0 when c equals 3. In general, so that's true if c is 3, but that's not always going to be true that it has those two zeros, because c is not always going to be 3. So we need to generalize that using the value of c. So in general, f of x has zeros at 0, c and -c, 0. And then the g function, g of x, has a 0 at 0, comma 1 over c. And that was the y-axis 0, and that's the only 0 that it's ever going to have. Part B says to identify the asymptotes for g of x, the blue function, and then describe how the rule for g, and the rule for g, what that means when they say the rule is that's just the definition of the function. So that's the 1 over x plus c thing. That's the rule of g. Describe how the rule of g can be used to predict the horizontal and vertical asymptotes of the graph. So let's see. First off, identify the asymptotes. Okay, so let's zoom in here a little bit. I can see on this function that there's going to be a vertical asymptote over here, and it might not be. It should be obvious, but if it's not obvious, I'm just going to put it in here. That asymptote is the line, vertical line, x equals -3, and notice how that's related to the value of c. If I were to put, if c is 3 in here and I have x plus 3, then a vertical asymptote happens whenever you can make the denominator equal to 0. And that's something that we talked about back in chapter 4. So if I have x plus 3 down here, then I know if x were -3, then I'd have -3 plus 3, and that gives me 0, and that makes the denominator 0, which means that we have a vertical asymptote. So the vertical asymptote is always going to be at the x value that's the same number, but the opposite sign of the c value. And you can see that when I change c, let me take this off. When I change c, that it moves the vertical asymptote to a different location. So right now, if c is 5, then x equals -5 would be my vertical asymptote. And if I made c -4.8, then if I made x negative, or actually this has to be +4.8, because remember we have to change the sign, then that's going to be our new vertical asymptote. But no matter where I change the c value, notice that the horizontal asymptote is always the x-axis. It's never changing off of that. And the reason for that is, again, something that we talked about back in chapter 4. So I'm going to go over to the concept summary from, this is chapter 4, lesson 2, and review horizontal asymptotes real quick. So the horizontal asymptote is based off the degree of the numerator and the degree of the denominator. And if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is 0. And that's what we saw. We had an asymptote of 0. So I'm going to go back and look at the degree of our function here. In the numerator for g of x, the degree of x, do you see an x? No, you don't even see an x. So x has a degree of 0 in the numerator. And in the denominator, we have x plus c. This x has a degree, a power of 1. So we have a degree of 0 on the top and a degree of 1 on the bottom, which means the bottom degree is bigger. Anytime the bottom degree is bigger, the asymptote will be the line y equals 0. So I'm just going to put in y equals 0 here. And you can see that even if I zoom in, I'm never actually going to touch this horizontal asymptote, because that's the concept of what a horizontal asymptote is. So let's pop back out and answer part B, the asymptotes of G. So G of X has a vertical asymptote at X equals -C, that's in general, and a horizontal asymptote of y equals 0. And that will always be true for this equation. It's always 0. It doesn't even matter what C is. Describe how the rule for G can be used to predict the horizontal and vertical asymptotes of its graph. So that's kind of what we did here in general. When I generalized this, I answered the second part. To answer the first part, technically, I think I should have used the actual value of C that I saw. So like right now, you can see on my screen, if I have C as 2.7, then the vertical asymptote would be X equals -2.7. Let's see, part C. How can you use the graph of F to predict the vertical asymptote in the graph of G? Oh, we already did that. We already answered that. Okay, so let's go over to look at our examples now. And I'm going to jump over to my other screen now. So I need to stop sharing on this screen and come over and share on my other screen. Ooh. All right, I figured out how to change my sharing settings. Okay, so now we can jump in and check out our examples for our lesson today. Okay, so example one, we're going to be talking about how to graph the tangent function. And the first question says, we're going to graph it. How can the unit circle help you sketch the graph of y equals the tangent of x? And so you can see on this picture that we're looking at only part of the unit circle. And you can see also that there is a video on this. So if you go on the online textbook and you pull up this lesson, which again is topic 7, lesson 5, and you watch the video, then you'll get their explanation. And I think this is actually a good video. You might want to go and do that on your own time and look at their explanation. But I'm going to just do the problem on my own. And then if you want to watch the video again on your own time, you can. But they have a really good way of showing this and good animations to illustrate how you graph the tangent function. Remember that when we talk about tangent functions, that tangent of x is the sine of x over the cosine of x. And in practical terms, when we're graphing that, that means that we're looking at the y values divided by the x values. So it is important, because we had just talked about in our warm-up about asymptotes, to think about when would the tangent function have an asymptote? When would the y values be equal to 0, or when would the x values be equal to 0? So if you look at the unit circle, I'm going to change colors and circle this. Up at pi over 2, actually, let me make this a little bit heavier. At pi over 2, we have this coordinate point 0, 1 with an x value of 0 and a y value of 1. So if I were to do y over x at that point, I would get 1 over 0. And anytime you divide by 0, that's going to give you a vertical asymptote. It's going to be an undefined coordinate point. And similarly, the same thing happens down here at negative pi over 2, or negative 90 degrees. If I did negative 1 over 0, I would also end up with something that's undefined. So anytime that you're graphing a tangent function, we can see the right side of the unit circle here. These are the only values that you want to use to graph your tangent function. We're going to go from negative pi over 2 to positive pi over 2. And I'm going to, just to show you, this is what they do in the video also, but I'm going to make an XY table and put my x values that you can see on the right side of the unit circle on the table. And then we're going to put the y values in as well. So in the middle, we have an x value of, actually, we're not doing the x values. Let me change that. I made a mistake. We are doing the radian measurements in the angles, so the angles of theta. So when I'm at 0 degrees, or 0 radians, that's going to go right in the middle. And then as I move up the triangle, not the triangle, the circle, as I move up the circle, then I would get to pi over 6, and then pi over 4, pi over 3, pi over 2. And as I move down the circle, I would be at similar values, but negative pi over 6, negative pi over 4, negative pi over 3, and negative pi over 2. And I'm going to add another column to my table. If I put actually, I'm not going to write the x values and the y values for each angle. I'm just going to do my y over x for each one of these. So if we look at the first one, for 0 degrees or 0 radians, then we're at the coordinate point 1, 0. Let's change to a color that they're not using. Let's use green. So if I'm at that point right there, if I do the y value over the x, I get 0 over 1, which is just 0. And then if I go to pi over 6, which would be this point right here, if I do the y over x, I would get 1/2 over square root 3 over 2. And remember, anytime the denominators match, you can just kind of ignore them. So this would reduce to 1 over square root of 3. But we're not allowed to leave a root in the denominator. So we're going to multiply the top and bottom by root 3 over root 3. And that leaves us with the square root of 3 over the number 3. So when I'm at pi over 6, this will be root 3 over 3. And when I'm at negative pi over 6, the only thing that changes is that becomes a negative sign, because you can see this negative sign right here in front of the 1/2. When I go to pi over 4, I have root 2 over 2 for both x and y. And when the x and y values are the same and you divide them, that's going to reduce to just the number 1. So at pi over 4, I'm going to have a tangent value of 1. And at negative pi over 4, I'm going to have a tangent value of negative 1. When I go to pi over 3 and I take the y value over the x, again, the 2's are going to cancel, and I'm going to have root 3 over 1, which is just root 3. And then down here, it will be negative root 3. And then finally, like we talked about already, at pi over 2, the tangent value is going to be undefined because we have 1 divided by 0. And it will also be undefined at negative pi over 2. So now we're going to graph this. And I'm going to go back to black, and I'm going to sketch a graph over here. And this will be 0. This will be pi over 2. This will be negative pi over 2. And then we'll put pi over 4. That's half of pi over 2. So we're going to put it halfway in between. And then we need a pi over 6. And a pi over 3. And we need those on both sides. Okay, so after you set up your x-axis, the next thing that you want to do is sketch your vertical asymptotes. And vertical asymptotes, again, are going to happen anywhere you see an undefined tangent value. And those for us happen at pi over 2. So we're going to do a vertical asymptote here and at negative pi over 2. So we're going to do another vertical asymptote over there. Notice, actually not notice, but I didn't put anything on my y-axis. So I'm going to put my y-axis information on here now. We're going to call this the number 1. We'll call this negative 1. Root 3 is about 1.7. And root 3 over 3 is about, I'm not sure. Let me think. 1.8. I think this is about maybe 0.57. I'm not 100% sure on that. I might be wrong. But even if I'm wrong, the location in general will be approximately the same. So what we want to do is graph all these things as coordinate points now. And notice our x-axis is in theta and our y-axis is in obviously y values. So at 0, I'm at the coordinate point 0. So let me I'm going to go big dots on here. I'm at 0, 0. At pi over 6, we're at root 3 over 3, which is about 0.57. And then I'd be down here at about negative 0.57. And then pi over 4, we're at the number 1. So let's go 1. Pi over 4, we're at 1. And pi over 3, we're at about 1.7. So let me go back over here and put, let's say that's 2, and that's negative 2. So we'd be, maybe this is about 1.7-ish. And at negative 3, let's say that's about 1.7-ish. And On first instincts, you might look at those dots and say, that makes a straight line. But that is not a straight line. If you drew a straight line in between those, you see, hopefully, that you would run into your vertical asymptotes. I'm just going to sketch that line real quick. So if you tried to draw a straight line through all that, boom, I just hit 2 asymptotes. And that is not possible because that's not what an asymptote does. You don't ever hit the line. So we need to take this line off. Don't sketch it like that. This is what a tangent actually looks like. The best way to do this is start at 0 and kind of, oops, I was still on highlighting, on erase mode, and I did not want to be on erase mode, so I accidentally removed my axes. Let's see if I can sketch these back in here quickly. Okay, I also took off my dot at 0. So let me put that back in. Okay, so if you start at 0, what you want to do is curve up to the right, kind of like you're making a parabola, but it's not actually a parabola shape. It's just a curved line. So you curve up to the right, and then you curve down to the left. And that is the graph y equals tangent of x. Or you could call it y equals tangent of theta, because I called it theta over here. But it's probably more appropriate to call it x. Okay, so that's your tangent function. I will say before I move on to the next example that if you wanted to graph y equals cotangent of x, because cotangent is the reciprocal of tangent, that you flip this graph over. So I'm going to do cotangent real quick in yellow. So we're going to do this in yellow. So on the tangent graph, if we go down to the left, cotangent is actually going to go up to the left. And if you go up to the right on tangent, that you go down to the right for cotangent. So cotangent and tangent look very similar. They're just flipped over. But the process is the exact same, except realize because you're flipping over the graph, instead of doing y over x, that for cotangent, you'd be doing x over y. But otherwise, it's the exact same process. All right, so now we're going to jump back to example 2. Okay, example 2. What are the key features, the domain, the range, the period, the zeros, and the asymptotes of the graph y equals tangent x? So if you think back to example 1, you saw that we started at negative pi over 2, and we went, I'm just going to draw a really small sketch. We looked at the right half of the unit circle, and down at the bottom we had negative pi over 2, and up at the top we had positive pi over 2. And if you go from negative pi over 2 to positive pi over 2, how far have you actually gone? Well, you can see this is half a circle, and half a circle is pi units. And so that is the period of a tangent function. The basic period of a tangent function is always pi. From last week, we talked about the basic period functions for sine and cosine, and those were both 2 pi. They both required that we looked all the way around the whole circle. A whole circle is 2 pi. But for tangent, you only have to look at half a circle, so your period is just pi. We also looked at the range when we sketched our function. So I'm going to sketch a function again real quick. Put some asymptotes, and your tangent function kind of went like that. And remember, the range is how far you move in the y direction. So you can see on this graph that we go all the way up to the right, up to infinity, and all the way down to the left, down to negative infinity. So your range is always going to be negative infinity to positive infinity. I think I skipped over the domain. Let me talk about the domain. The domain in general is from negative pi over 2 to positive pi over 2. So I didn't really skip over it. I talked about it. I just didn't call it the domain. The period we've already talked about is pi. So we have domain, we have range, we have period. The zeros. you can see on our graph that the only 0 we had was at the origin. So in general, we're going to have a 0, 0 origin, or not 0, 0 origin. Obviously, it's 0, 0 the origin, but our 0 is 0, 0. And asymptotes, we have an asymptote at x equals negative pi over 2 and x equals positive pi over 2. And remember, those are both vertical asymptotes, and there is no horizontal asymptote on a tangent function. So we've answered all the questions for example 2 now, all the parts of it. But we haven't fully answered for every possible graph. And the reason for that is when we looked at example 1 and we only looked at the right side of the unit circle, that gave us one period of a tangent graph. And if you think about last week, when I graphed sine and cosine functions, a sine function looks like that. And what I just drew is one period of a sine function, a sine wave. But the sine function doesn't just stop there. It keeps going, because remember, we can continue moving around a circle many times. You don't have to only go around a circle once. You can go around multiple times. So this sine wave continues moving along the x-axis, and it goes on and on forever. So this right here, that's one period. That's a second period. That's a third period. That's a fourth period. And for sine, our periods were always multiples of 2 pi. So I could have a maximum here, but then I could add 2 pi to it and get another maximum here. And then I could add another 2 pi and get a maximum here. And the same kind of concept works for tangent, except realize because our period is only pi units, that we're only adding multiples of pi rather than 2 pi. So while we have a 0 at 0, 0, we could also have another 0 at 0, or not, oops, let me erase that, because this is moving in the x direction. We could also have another 0 at pi, comma 0, and then we could have one at 2 pi, comma 0, and then 3 pi, comma 0, etc. And notice every time I'm just adding pi to the x value. For the asymptotes, I have an asymptote at negative pi over 2 and then positive pi over 2. But if I added pi to that, then I would get 3 pi over 2. And if I added pi to that, I would then get 5 pi over 2. And if I added pi to that, I would then get 7 pi over 2. So the same way that you can draw multiple cycles of a sine or a cosine graph, you can also draw multiple cycles of a tangent graph. So I'm going to sketch that over here. And let me put up some asymptotes. I'm going to do my asymptotes in black. So let's say that's negative pi over 2, that's positive pi over 2, that's 3 pi over 2, and then 5 pi over 2, and then 7 pi over 2. I'm just going to put these up top for space. And then I'm going to sketch my curves. So I go up to the right and down to the left. There'd be a 0 in the middle, up to the right and down to the left, up to the right, down to the left, up to the right, and down to the left. So you can see what I just did is I drew 4 periods of the graph of tangent x. So you can draw multiple periods. It's possible to do this, but generally if I ever ask you to graph something, if your pre-cal teacher next year asks you to graph something, they're usually only going to ask you to draw one period of whatever function that you're looking at. So it's possible to draw multiple periods, but usually you only have to draw one. But it's important that you understand how it works. And so as a result, your zeros, because they're happening every pi units, you can say you have a 0 at 0, 0, but you also have zeros at every multiple of pi, comma 0. So k is some constant. And if k is 0, 0 times pi just gives you 0. That would give you this first point. If k is 1, it would give you this point. If k is 2, it gives you this point, et cetera, et cetera. And k can just go on and on forever because it's just showing you that you're moving around and around a circle. Similarly, the same thing works for the asymptotes. The way you can say this is you could start with your left asymptote, this one. You could say that you have asymptotes at negative pi over 2 plus k pi. Every multiple of k is going to give you another vertical asymptote, like we saw in the graph that I did where I drew 4 periods of tangent. So those are key features of a tangent graph. Okay, now let's check out example 3. Okay, example 3, now we're going to look at a translated, a shifted, a modified tangent function. And this time we're looking at a times the tangent of bx. And that should look really similar to you because we talked about the same format last week when we did sine and cosine. We did a times sine or cosine times b of bx. And remember before that a, when we did sine and cosine, was the amplitude, and b wasn't the period by itself, but 2 pi divided by b was the period, but that was only for sine and cosine. It should stick out to you right away that there's no way that the period is going to be 2 pi over b for tangent, because the period of a tangent function is not 2 pi. It's pi. So for us, remember now that our period is going to be pi over b. And amplitude refers to how high or low a sine or cosine wave can go. But tangent functions, like we looked at in example 1 and 2, they go up forever and they go down forever. So a is no longer considered the amplitude, but it does show us the stretching factor, how much the graph gets stretched high or low. So a is now just going to be, we're going to call it like a stretching factor. And remember again, also, if a is negative, then it flips the graph over. So it can also have that power, that ability to do that, but don't refer to a as the amplitude when you're talking about tangent or cotangent, because it's not the amplitude anymore. So they don't give us an actual value for a or b here, so we're just going to come up with one. We're going to make one up. And I'm going to use a is 2 and b is 4 for our function. So that means that we're going to look at the function y equals 2 tangent of 4x. And we're going to see, what does that do to the graph? So based off what we have here, let's first draw, the first thing I want to draw is a set of axes. So let me draw a set of axes over here on the right. And I'm going to make this be negative pi over 2. And this will be positive pi over 2. And let's draw some asymptotes. Actually, I'm going to draw my asymptotes in green. And I should have drawn some stuff on the y-axis. So let me draw some y-axis values. Let's say 1, 2, 3, 4, -1, -2, -3, -4. Okay, so what I'm going to do first is I'm just going to draw a basic tangent graph, and I'm going to do my basic tangent graph in purple, just y equals tangent of x. Remember that that goes through the origin, and it goes up to the right, and it goes down to the left. So let's now draw 2 tangent of x, and we're going to do that in blue. So remember, our period is pi over b, and our b value is 4. So our period now is going to be pi over 4. And so that's in here, that's half of pi over 2. So I'm going to have an asymptote now that happens halfway. So what that should tell you immediately is that our function is now being shrunk inwards because it's half as long as a normal tangent function. Also, so then again, we're still going to be in the middle, in the very middle at the origin for this. And all of our normal points are going to be multiplied by 2 because we have this a value of 2. And I don't want to do too much without writing this down. So I'm going to write my stuff down. Remember before that we had our theta values that we looked at? We went from negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 2. Oops, not 2. This should be a 6. 0, and then positive pi over 6, pi over 4, pi over 3, pi over 2. Those are the theta values that we used for a regular tangent function. But we're not using a regular tangent function anymore. We are now doing one that got shrunk in half. So when we shrink this in half, when we take our b value, and b is now 4, you can see that it cut our graph in half. It's half as wide as it used to be. So we're going to use theta values over 2. So I'm going to now have negative pi over 4, negative pi over 3 times 2 is 6, negative pi over 8, negative pi over 12. This will still be 0, and then this will be positive pi over 12, 8, 6, and 4. So these are the values that we're going to be using to sketch our points. And our tangent values, which are y over x, they're all going to be multiplied by this number of 2. So before, this was undefined. If you multiply something that's undefined by 2, you still get something that's undefined. Before, the negative pi over 6 was a negative root 3, but I need to multiply that by 2. So that's going to be negative 2 times the square root of 3. Our pi over 4 value before was 1, but if we multiply that by 2, we're going to get 2. Our pi over 6 value was negative root 3 over 3. So if we multiply that by 2, we get negative 2 root 3 over 3. 0 times 2 is still going to give me 0. And then these will just be the positives of the ones that we've already done. So 2 root 3 over 3, 2, 2 times the square root of 3, and then something that's undefined. Okay, so to sketch this on top of the same curve, I'm going to do my 2 tangent 4x graph. I'm going to do it in black, just so it sticks out a little bit more. We are still in here at 0. I know this is going to be kind of hard to see, but this is going to be pi over 8 and negative pi over 8. So those values are negative 2 and positive 2. So here I should be at 2, and here I should be at negative 2. And I'm just going to kind of sketch through that and through that. So you can see the graph has the same behavior, but it's squished in and it's also stretched taller. Normally, if I go for the purple one, the basic one, tangent x, I have to go over halfway between 0 and pi over 2 to go up 1 unit. But for the black graph, for the 2 tangent 4x, when I go halfway over between 0 and pi over 4, halfway between my x-intercept and my vertical asymptote, now I go up 2, whereas before I only went up 1 because of that stretching factor, the a value. So just realize that when you have a b value, you need to correspondingly adjust your period. And when you have an a value, you need to correspondingly adjust your stretching factor. If the graph is It could get stretched taller when A is bigger than 1, and if A is smaller than 1, meaning it's a fraction like a half or a third or 2/3 or 4/5 or something like that, then it would get compressed. It would get shrunk down, kind of like maybe like a sumo wrestler was like sitting on the function, just got squished down. So that's example 3. Now let's check out example 4. All right, so example 4 was our word problem. We're going to model a trig function based off real life stuff. And it says Seth is observing today's rocket launch at Cape Canaveral. If you don't know, Cape Canaveral is down in Florida. It's one of the NASA sites, and it's actually back in, I think, 1990, maybe it was. They actually had a rocket launch down there that the rocket blew up as it was launching. And it was pretty sad. I don't really remember it because I was like 5 years old when it happened. But I have like vague memories of it happening. But let's not talk about sad things right now. Let's just do this problem. So Seth is observing today's rocket launch at Cape Canaveral from the viewing area about 3 miles away. Write a function to model the height h of the rocket as a function of the angle of inclination theta from Seth's position in the viewing area to the rocket. Identify an appropriate domain and use the function to describe the motion of the rocket. So you can see in this picture here that they've drawn for us a triangle overlapping, the real thing that's happening. So I'm just going to take this triangle and sketch it out over here. This is our angle theta. This is 3. This is the height. I don't know the height. We want to come up with a function to model the height. That's what it says in the problem, that we need to write a function to model the height h of the rocket. So when you see a triangle in here, hopefully you can think back to the trig stuff that we've been talking about in this whole chapter. And when you see an angle theta, you want to know, well, what side of the triangle is this letter h? What side is the number 3? So h, you can see, is all the way across on the other side of the triangle. So it's the opposite side. And this 3 is right next to your angle theta. It's the adjacent side. And because this side over here is across from the right angle, that it has to be the hypotenuse. And we don't care about the hypotenuse here because we know the opposite side, we know the adjacent side, and we know that opposite over adjacent gives us the tangent ratio. So our equation is going to start off by saying the tangent of theta is the opposite side h over the side we know, adjacent 3. And then we need to come up with our function to model h. We want to get h by itself. How do you do that? You multiply both sides by 3. So h is going to be 3 tangent of theta. And that's your function. And that wasn't really hard at all. We need to identify an appropriate domain. So we need to think about what angles of theta could this rocket move through. And remember that when we talked about tangent graphs, we were thinking about the right half of a unit circle. So positive angles happen up here in quadrant 1, and negative angles happen down here in quadrant 4. Well, what kind of angles could this rocket go through? If it's sitting on the Earth and it's launching, it should be obvious to you that the rocket's moving up, that it's moving through positive angles. The rocket is never going to go down into the Earth. Like, that's not possible. It doesn't make any sense. So we're not going to look at anything down here in quadrant 4. We're only going to look at the quadrant 1 angles. So our domain is going to start at 0 degrees or 0 radians, and it's going to move up just through the quadrant 1 angles, which is up through pi over 2. So that's in radians. If you were ever wanting to think about this as degrees, it would be 0 degrees up to 90 degrees, and realize that's in degrees. Use the function to describe the motion of the rocket. Well, the rocket moves up, goes up in the air. I'm not really sure what to do with that. There was something, if you go and pull up the online textbook for yourself and you read through, if you click on this solution button over here, if you click on that, it will talk. One of the things it talks about is realize that the rocket is just going straight up into the atmosphere. It's moving like this. it's not actually moving along the unit circle. The rocket's not doing this because it's not going to get closer to you. I don't know. The thing that it says in there is that remember that the rocket is always 3 miles away from you. It's not going to like come close towards you. It's just moving straight up. So even though in order to graph a tangent function, we would need to be thinking about, oh, we're moving around the unit circle. When you graph like the real life motion of something, it's not necessarily going to follow that same motion like that of a tangent function. In real life, some object might just go straight up in the air, or it might go straight sideways, or it might be defined along some different specified curve, but it's not usually going to follow the actual tangent motion of a tangent graph. And if that's something that interests you, here's the stuff that you want to focus on. You want to go take physics. You want to do engineering stuff when you go to college. But if stuff like that is interesting to you, those are the areas that you want to go to. You want to go look at physics, and you want to do engineering. Physics is a class I took in high school. I took physics and AP physics. Even though it's science, you do a lot of trig, you do a lot of pre-calculus, you do a lot of calculus in those classes. Physics is basically just math applied to real life. So I really enjoyed physics, obviously, because I'm a big math nerd. So I liked physics. I liked applying math to real life scenarios. But for all of you guys that sit around and you say, you know, when am I ever going to use this math in real life? Like, how is this applicable? You can see a lot of real life applications to math concepts in your science classes. Maybe not quite as much in like biology, although there's some, but you definitely see a lot of it in chemistry. I think about balancing equations. I think about, you know, making compounds of stuff, computing the moles, for example. Definitely chemistry, definitely physics. Those are very heavy math science courses. So that's example 4. We've got one more example to look at. And example 5 is on graphing a secant function. So the focus of this one is to graph a secant, but I'm also going to show you, or at least talk about how to do a cosecant function. So what we want to think about is if we're going to be graphing a secant function, secant is the reciprocal of what? And if you don't remember off the top of your head, I will tell you that secant is the reciprocal of cosine. So they want to know, how is the graph of secant x related to the graph of cosine x? And if you didn't come up with this, you could have seen it from the fact that they ask it in this question here. So the purpose of this is to graph the function. So what we're going to do is I'm going to show you a cosine function first, and then show you immediately how you can get a secant function. And it might seem difficult going into the question, but it's actually a really, really simple concept. So let's draw an axis, and you remember that sine and cosine functions both have periods of 2 pi. And we're going to split this into our 3 quadrants, our 4 quadrants. Sorry, I don't know what I'm saying. Okay, so that's basic stuff of what we need. We know that a cosine function always starts at 1. Let me go with a heavier dot. Then it goes to 0. Then it goes to -1, back to 0, and then back to 1. And now let's sketch a curve through this. And realize it keeps going in both directions. So that's your basic cosine function. So the first step to graphing a secant is graph a cosine function. Second step, everywhere cosine of theta is equal to 0, draw a vertical asymptote. And you might wonder, why? Why would I do that? Well, if cosine is equal to 0 and secant is the reciprocal of cosine, what's 1 over 0? It's undefined. So any place that cosine is equal to 0, your secant function is going to be undefined. It's going to have a vertical asymptote. So that means that we need vertical asymptotes through 3 pi over 2 and through pi over 2. All right, step 3 is sketch, let's call it the opposite of cosine. So let me talk about what that means. What is the opposite of cosine? So I don't actually mean the opposite. I mean technically like the reciprocal. So what you want to think about is let's look in this middle section in here, in between the 2 purple lines. On this interval, you can see that the blue function, if I start from the middle, if I start from right here, that if I look to the left and the right of that point, the graph moves up, goes up to the right and up to the left. It goes, we're below the x-axis. We're moving up towards the x-axis. So the cosine, the secant of that is going to do the opposite. It's going to go farther away. So we start here, and instead of moving up, we go down. And we go down. And that's one piece of a secant graph. Then if you were to come over here to the next point, on this section, the graph is going down for cosine. The blue graph is going down. So you want to move up. And then on this point over here, you can see that your blue graph again is going down. So you want to go up. You want to go up. And then if I were to continue this graph, just, I kept on going forever, whatever, that I would just continue going away from the cosine graph in order to sketch secant. So here I have a minimum. I'm going to go down and go down. Here I have a maximum. I'm going to go up and go up. Minimum, go down and go down. Maximum, go up, go up. And that's all you have to do to graph your reciprocal function, your secant function. Remember, if you're going to draw all these extra periods that you need to continue drawing your asymptotes, so there would be another asymptote in here, there would be another asymptote in here, there'd be an asymptote in here, and there'd be an asymptote in here, etc. So that's how you graph secant functions. And it's really the exact same concept if you were ever going to draw a cosecant function. So if I had y equals sine x versus y equals cosecant, oops, I'm spelling cosecant wrong. Cosecant is CSC of theta. Let me do thetas for both of these. So boom, 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 boom. Okay, so sine graphs, they look like that. So what I would want to do now is everywhere my sine touches 0, I'm going to draw asymptotes. And same concept as what we did for secant, you want to go away from your function. Let me pull this over a little bit so you guys can see it better. So I'm going to do this one in, ooh, let's come up with a different color. I don't know, let's go with orange. It's kind of an ugly orange, but whatever. So you find a maximum. We have this point here. Your red graph goes down right there, so we're going to go up. Find a minimum. Your graph, the red graph goes up, so you go down. Find a maximum, the red graph goes down, so you go up. Find a minimum, the red graph goes up, so you go down, etc. And that's a cosecant function. That's cosecant of x or cosecant of theta. And you can see, you know, these two things, the orange graph and the red graph for cosecant and secant, they look basically the exact same. It's the only thing that's differentiating between the two of them is the x value. Because sine and cosine are the exact same graph, they're just shifted a little bit. The same thing is true with secant and cosecant. They're the exact same graph, they're just shifted a little bit. And that little bit is dependent upon your b value that's in the function. So remember that we have like y equals a sine bx. This b value is what determines how much that shift happens in your function. All right, so that's the last example. Real quick, I'm just going to pull up the summary for the lesson. So you can see on here that we have the tangent is sine over cosine. You know that already. The cotangent is a reciprocal of that. It's cosine over sine. Secant is the reciprocal of cosine. Cosecant is the reciprocal of sine. And then they've drawn graphs for all of these functions. They're not as pretty as mine. Obviously, mine they're just freehand, so they're not perfect. If you want really pretty, perfect stuff, go sketch something over on Desmos, and you'll see really beautiful, pretty graphs. They also talk about some key features in here, and I'll let you guys just read that for yourselves. But that's the whole lesson. That's lesson 5, graphing other trig functions besides the sine and cosine functions. But realize that in order to graph the other functions, sometimes you need to draw a sine or a cosine function first to have a reference point in order to draw your reciprocal function. All right, hope you guys have a good week. And if you guys have any questions on the assignments for this lesson, don't hesitate to contact me.